talk briefly about springs and Hooke's law and how we can use masses put on the end of these springs to determine the spring constant in each one of these. And then in your lab, you're also going to be able to rank these from least spring constant to the greatest spring constant. So starting off, one of the things I want to point out to you is that if I take 1 kilo or 1,000 grams, here I'm going to put this on the end of this red one, and we'll kind of prevent it from bouncing, and you kind of see how low that guy gets. And then we'll take on another kilo. It does look a little different, but it is massed at 1,000 grams, and then we'll put that there. And then we'll look at another kilo and put it on this other spring, and we'll kind of see that there. Now, you will notice that they hang at different lengths. So what we are going to note, what we'll note here is that each one of these have different stiffness, and that is their spring constant. So right now, this guy right here and this one, they're not bouncing up and down. They're staying in equilibrium. So that is the force. The net force on the object is 0 here. Gravity is going to be pulling down on each one of these guys, and the force of the spring is pulling up. So we have a net force on each one being 0. So to be able to find out the spring force that's acting on each one of these guys, we find the weight of the mass on the end, and that will be equal to the spring force. Okay. Now, one of the things I want to point out to you when we look at Hooke's law, okay, we have an equation of the force of the spring is going to be equal to negative spring constant times the displacement. So if I change the displacement, it is directly going to affect the force. So here, as I move it here, I have a little force. And as I keep making the displacement bigger, I am going to generate a greater elastic force going back. So what we'll end up seeing here is that as we increase the mass on the end of this, there's a greater force of gravity, yes. But that also means that we stretch this out more, and therefore a greater force of elastic force going back in the opposite direction. That's why I can put a kilo on the end of this guy and actually stretch it out. But notice, once I let go, it's not really moving that much. It goes back and forth a little bit because of the vibration of the spring. But what we should note is that we've stretched out the spring. If I were to remove the kilo, it's just like letting go of the spring, and it would come back. And then that's what we are talking about. We want to know, what is that force coming back up, the elastic force. To do that, we have to know what each one of these springs are, spring constants of each one of these guys are. And then we're going to rank them. That's the plan. So I'm going to kind of take a moment to pause the video. I'm going to go through and jot down some information that I collect so that we're not having to go through the whole lab of each one of these guys. But one of the things that I want you to note is we're going to put on several masses on the end of each one of these springs, and then we're going to plot those points. As we plot those points, we should be able to interpret a relationship and hopefully find the slope of a line that might give us our K value. Okay, so one of the things I want to point out to you is that I've got a T-table here. I have made the X, or the displacement, the amount I changed my spring, I made that the independent value, and then the dependent value depends upon how much I stretch the string is going to be what that force is. Now, we are going to take this data and then we're going to graph it. I'm going to show you a digital graph off to the side in just a minute, and we need to find the slope of that line. The next thing I'm going to do is I'm going to go through and I'm going to show you what is the white, what is the green, what is the yellow, what is the blue table numbers as I put on these masses. If you notice right here, I started with 200 grams, which comes out to 1.962 newtons. If you will look at that, what I did is I took 200 grams, divided by 1,000, and multiplied by 9.81, which is the accepted value of average of acceleration due to gravity. And that'll give us the weight of this object. And then I added on For the next one, I added on 50, so it was 250. The next one, I took away the 50 and added on 100, so that would be 300, and that was 300 grams. And then I took off I left that 100 on and I added on 50, so that it would be 350, and then I took those off and put on another 200, so that it would be 400 down here at the bottom. That's going to see you're going to see these values repeated because I'm going to do that on every single spring. So that force will be what is on every single spring. But we'll have different distances as which they stretch based upon that force. We'll get right back.
Okay, as you see here, this is the graph we made for the red spring. The slope M is 24.5. That means that is your K value for the red spring.
So now we're looking at the white. I have added in the displacements as I went in and added on the masses of the specific weights. I got a different set of numbers here for the displacement. Something to note that the change is not as drastic as it just was. We're going to graph these out. Now to the side, you should see that graph right now of what we had there. We're going to move on now to green.
This is the data collected for the white spring. As you see, the slope there on the white spring was 39.5, so roughly 40. That is your K value for the white spring.
All right, so now we're looking at the green. You should note that the green's displacement is considerably less than the white and the red, which means that the green has a higher spring constant than the other two. So there's the green data. We're going to move on now to the yellow data.
Here's the data we collected for the green. As you see, we found the slope of the line. That's the M value. The M is 50.0. That is the K value for green.
Okay, so here's the data collected for the yellow. A little bit different data. Resembles more of the red than it does the white or the green. So if I have to make some connections for right now, it would look like the red has the least amount of spring constant because it has the greatest change. Then the yellow has the next greatest change. Then the white has the next. And the green was the one that changed the least. I still have one more spring. We're going to put the blue in there and see where he goes in. And then we'll go.
Here's the data we collected and graph for the yellow. The slope of this line is 32.9, so roughly 33. That is your K value for this spring.
Blue is going to come in with these numbers, very similar to green. So it looks like from least to greatest, we would go red, yellow, white, blue, green. But let's go back and look at the data and make sure, and we'll get a nice, good ranking of our least spring constant to our greatest spring constant in the correct color order.
Here is the data collected for the blue spring. It has a M slope of 29.9, so that is your K value for the blue spring.